Welcome, dear students. Today we are going to see what an assembly language is. This is part of our course in compilers, and we will have 2 or 3 videos on assembly languages. Today we are going to see assembly language in comparison with machine language. So what is an assembly language? An assembly language is a programming language. First, we should make sure that an assembly language is a language, not a hardware, but a software. And it consists of instructions, and the instructions of assembly language are called as mnemonic codes. And each instruction in the assembly language that corresponds with an instruction in the machine language. So machines basically understands machine language, and corresponding to each machine language, the assembly languages are mimicking the instructions of machine language. And therefore, we have an assembler. An assembler is a software, or you can say this is a language processor. This is a language processor because there is a translation from assembly language into object code, that is the machine understandable language. Hence, an assembler is a language processor that translates the source code, which is written in assembly language, to a machine understandable object code. We have a beautiful picture here. We have a source program that has its language as assembly language using mnemonic opcode symbols and some data, which is put into an assembler, which is a language processor, and the output of the process is an object code, which is basically a machine understandable language. What is a machine language? Machine language is simply a collection of binary digits. You can say it is just zeros and ones. The machines understand only zeros and ones as current positive or negative or presence and absence of electricity. Another names for machine language are object code and machine code. So either way you refer to object code or machine code, everything refers to this binary digit format of the machine language. And machine language is the only language a machine is capable of understanding. Even if we program in a C or Java or we do in assembly language, it needs to be translated into the machine language. And this is the lowest semantic level. So by lowest means there is nothing beyond this language. So this is also called the first generation of language. First generation of language is this machine language. For example, you can see some zeros and ones here, which basically translates to hello world. Maybe when you begin your programming, the first thing most of us have often undergone is to print hello world. And this is the exact representation of how each of these alphabetic things can be represented in a machine language. Now the question is whether the machine code has a structure. Yes, it has a structure. It has an opcode, as you can see in this figure here, and it has an operand address. An opcode means an executable operation, some instructions for some actions to be taken into account, like load or move, add, subtract. There are various instructions. All these things are meant by the opcode. And we have the operand address. Operand address basically refers to a constant value or a memory address in the form of a register or a storage location. Then the architecture of the processor determines how the instructions are patterned. There are various things referred by the term the architecture of the processor. Maybe in your earlier studies you have heard about ISA. ISA refers to the instruction set architecture. So it basically means that assembly language is not just one language. Each CPU differs in its structure. You may be knowing 8086 and its instruction set is different from 8085 or the 386, which is basically the Pentium format. Then we have the old Motorola, and we have ARM or the ARM architecture. We have the AMD architecture. So basically there are differences between and among these processes. The opcode and operands may be different in each one. The instruction set length is different. The earlier ones we had 16-bit, Then we had 32-bit, and presently we have 64-bit and even 128-bit architecture. And there are differences in addressing the registers and memory, the external storages, everything. So everything is meant by the term, the architecture of the processor. Now we have another question. Can we write a program in machine code? I'm just giving you a second to answer this question in your mind. Yes, it is not impossible to have a machine code language used in some devices, but that is highly improbable. It is because of this difficulty in programming that we moved from machine code to assembly languages, maybe for the purpose of tweaking some hardware or enhancing its performance. Still, we can program in the machine code, but the same thing we do with machine code can be done by assemblers, which gives us more flexibility. So the answer to this question is, it is possible, but it is a rare, maybe a very rare situation that we program in a machine code. Then now we see why we move from this machine code to assembly code. The first answer would be the easy coding. It is not an easy task to code everything in zeros and ones, looking into some table and referring to all the opcodes and operand address from some references only in zeros and ones. That is not understandable to the human level. So we needed some mechanism that can mimic the instruction set, and we have the assemblers. Then this is a gradual development of the programming language. As we are familiar, every language has its development. The language we speak right now may not be the language that was spoken 50 years back or 100 or 200 years back, whether it is the case of English, French, or Malayalam or Hindi, anything. Development is something natural in each language. This is the case with our programming language too. The first generation of programming language, which was the binary codes or machine language, and due to its difficulty, we moved to second generation of language, and this second generation of language is called the assemblers. From assemblers, we moved to the third generation of language that is commonly referred to as high level language. Maybe you are familiar with the term HLL, which refers to high level language. So we have C or Java or such languages which are high level language. Then there is another classification for a fourth level of language. This is basically scripting language. Okay, these are used for scripting in web or such developmental things. And some examples are like Python or PHP. All these are scripting languages. Then we have a fifth generation of languages, as per some experts, that is basically AI-based language. Okay, so this is part of the development of any language. And you can see an instruction set here. This is taken from a 32-bit architecture IA32 instruction set. There you know the first general purpose register. It has a 32-bit address. Let me just draw it. And this is EAX, the EAX. And it is divided into two 16 bits, that is AX. And this 16-bit again can be divided into AH and AL. This AL in the lower section is the accumulator. And this is an instruction. You can see all the zeros and ones. And the first five, these up to here, this is an instruction to do something. This is an instruction for load. Okay, load something in the IA32 architecture. And here you can see the three zeros. Okay, let me cut those zeros. I have put it down. And this is referring to a register. So as there are three zeros, it can refer to 8 registers. This is the accumulator or the AL. And if we calculate this value, this binary value into our decimal system, that is 96. Okay, so 10110, that is an instruction to load something. 000 refers to the AL register or the accumulator, and this 8-digit number refers to the value 98. And Making this into assembly language just means move AL61H. This 61H is basically a hexadecimal number, and 61 in a hexadecimal is equal to 97 in the decimal. So move AL61H means in the assembly language means load the value or 97 into the accumulator. And for that, we need to type the 16 zeros and ones in the machine language. So that is what is meant by the easiness of coding, and this is the gradual development in the programming language. The elements of assembly language. An assembly language is a machine-dependent language, and it is still a low-level programming. Maybe there is an advancement over the machine language, but still, assembly language is a low-level programming. There are three main features that distinguishes it from the machine language. The first one is the use of mnemonic operation codes, and the second one, it uses symbolic operands, and third one, data declaration became so easy. So what is mnemonic operation code means? Mnemonic operation code means all the instructions to perform something which was used in binary digits using zeros and ones, we can represent all those instructions with English like words like move or load, add, subtract. So that is what is meant by mnemonic operation codes. And this facility eliminates the need to memorize the things which was otherwise written in numbers of zeros and ones. Then the use of symbolic operands, not only the instruction but also the data can be represented using some form of symbolic representation. In the high-level language, we use variables and other things. We just say int x equal to 10. In fact, this x stands for some memory location that we do not know. The memory binding is done automatically by the machine. In the same manner, assembly languages provided us with some facility that we need not be worried about the memory location. Symbolic names can be utilized to represent both data and instruction. And we don't need to know the details regarding memory binding. And the third thing, data declaration. Data could be declared in a variety of notations, including the decimal notation. Just imagine you had to represent a simple word minus 12 in assembly language. You can do it easily. Instead, if you were doing that in a machine code, first you have to represent whether it is plus or minus using some 4 or 8 digit zeros and ones. Then you have to find the value for 12, and it was so hectic. Or just imagine you just want to print the word 14.5, and it becomes uh, all the more difficult when you do that in the machine code. But the assembly language, it provides us the ability to represent this directly in the decimal notation. What is the structure of an assembly language? Here you can see four things: a label, the mnemonic codes, operand, and comments. In fact, the first label and the comment should be in square brackets. A square bracket implies that this is an optional thing, not necessary. Label means giving a name or assign something, assign a label to address something. Mnemonic opcodes, basically they imply what action is to be performed, an action to be taken place. Operands may mean a variable or an address. Then we have comments which are really optional. And here we have it in its true form, like it comes in the square bracket label, opcode, operand specification, and there is a comment. Okay, comment comes here. For the operand specification, it has the following syntax. There's a symbolic name, the displacement, and index register. You can see an example given here. You have area, area plus 5, area in brackets 4, then area plus 5 and 4. Okay, just remember that even in our high-level language, a variable is a name given for a memory reference. We don't know how many locations are there in our main memory. Maybe from 1,000 to 100,000, there are many memory locations. So to address it directly, we give names, we give variable names. For example, we have area. Just imagine in your main memory, you don't know an address location. Maybe that address location for the sake of learning, just imagine this is 10,000. Okay, the area begins at 10,000. Then there are many things. Area plus 5 means, think about area just like an array. There are some 10 or 100 steps, arrays coming upon here. This is area 0, 1, 2, 3, 4, 5. Then start from area and add 5 to it, and we have area plus 5. Area, and in brackets a 4 is given. When there is bracket, this means the index register. There is special index register in every CPU, and an index register may contain some numbers. Just imagine in the fourth index register, there is a number called 10. So from area, you have to move to the 10th position to find something from that memory location. And you can combine both displacement and the index register. So maybe the index register refers to 20 and 5 is just 5. Area begins in some 10,000. So you have to go to 10,000 plus 5 plus 20, and from there you will get a value. So that is how the operand specification is addressed here. This is an example of mnemonic operation code. We have stop, add, subtract, multiply, everything. And the same thing can be represented using our machine code. Just imagine you have some 8 zeros here instead of just 2 zeros to represent stop, and the final 0 and 1 to represent add, 1 1. There are 6 zeros behind this to represent it in the machine code. So it goes on like that, and this representation for conversion to this short form is so easy. There is an example given for the opcodes. I just remind you about it. We have the mnemonic opcode move. Move basically means that's a transaction of something between memory and a register. So when we have mover, you just see the final alphabet here is register. So if it is mover, it means that you are transferring something from memory to the register. And if the final alphabet, the move M, in move M, the final alphabet is M, and we are transferring something from the register to the memory. So the final word, whether it is R or M, shows the destination. All arithmetics is performed in the registers. Mostly it is in the accumulator, and it replaces the contents of the register. And we have some conditional codes too, conditional codes and branching, and that needs its performance later. Some verification is to be taken place before the addition or subtraction is done. We have comparison and branching. This is an instruction set format. We have a sign which is not part of the instruction. 2 bits are reserved for opcode, 1 bit for the registry operand, and 3 bits are reserved for the memory operand. Then we have the conditional code specified in the branching condition. There are at least six specifications. This LT here implies less than, okay? LE less than or equal to, EQ means equal to, GT greater than or equal to, and we can represent all these things. In a machine language program, all addresses and constants are shown in decimal. Okay, you have it shown in this table. everything, every thing can be, decimal values can be placed as decimal. And we are coming to the final slide of this presentation. We have some question. Do we still need assemblers? Since we have fourth level languages and artificial intelligence based languages, do we need assemblers? Yes, the answer is a true yes, because at the design of CPU, we need assembly language to be implemented to it. If there is no assembly language assigned to the instruction set architecture, we cannot perform any high-level language into it, because as a part of compilation, we need to break it down into opcodes finally, for which we need the help of assembly language. Then secondly, to tweak the hardware, we need assembly languages. You know that assembly languages can directly interact with the inherent power of the machines. So to enhance some capabilities of the machine, of your hardware, we need assembly language. Then, as part of compilation, every high-level language is to be converted into object code. Later, we will see that each instruction set as an intermediate representation needs to be converted into machine-dependent language. We have machine-dependent intermediate languages, and there we basically depend on the assembly-like languages. Okay, machine-dependent language. Then, the final thing regarding assembly languages is that the more we know regarding the assembly language and the structure of the processor, the more we know about how a machine works. Peripherally, we know many things, but how the instructions are processed, how things happen, how addition is made, how subtraction is made, how a command is converted into an executionable action within a processor, it gives us a bigger picture of how a machine works. So in the next lecture, we will see more details about assembly languages, and this was the first part. Thank you for listening to me.